like mass, length, time and temperature. But what is a physical quantity? If a quantity possesses these two properties, then it is a physical quantity. Its numerical magnitude and the unit in which it is measured. If we say that the height of a student is 165 centimeters, then it is representing both the properties of a physical quantity, i.e. 165 is the numerical magnitude, while centimeters is the unit in which the height is measured. Remember, if we only state height as 165, then it is not a physical quantity, since it does not tell us about the unit in which it is measured. So it is a must for physical quantity to have both magnitude as well as unit. Physical quantities are divided into two categories. Base quantities. Base quantities form the base or foundation of other physical quantities. In other words, the quantities are the basis with which derived quantities are expressed. These quantities are length, mass, time, temperature, intensity of light, electric current, and the amount of a substance. Derived quantities. Derived quantities, therefore, are those which are expressed in terms of base quantities. These quantities include area, volume, velocity, acceleration, force, pressure, momentum, electric charge, electric induction, etc. Before talking about the units which are associated with base and derived quantities, we need to know about the universally adopted system of units for physical quantities. This is to be noted that measuring does not always involve counting. Like if we need milk, we need to understand what quantity of milk is required. Similarly, to describe the physical quantities, a standard is required with which the quantities could be compared and expressed. This standard in physics is known as a unit. By that time, it was crucial so that the knowledge and findings with the advancement of fields could be shared universally by adopting some known standards. In this context, during the 11th General Conference on Weights and Measures held in Paris in 1960, a universal international system of units was accepted. This system is commonly referred to as SI, System International. Now, coming back to the base and derived quantities, we have understood about these quantities. Now, we will have a look at the units in which these are measured. Base units. The units used to measure base quantities are called base units. We now know that base quantities are 7 in number. But in what units these quantities are measured? Well, length quantity is measured in meter. Time is measured in second. Mass in kilogram. Electric current in ampere, temperature in Kelvin, amount of substance in mole, and intensity of light in candela. Derived units. The units used to measure derived quantities are called derived units. They are defined in terms of base units. We get them by multiplying or dividing one or more base unit with each other. For example, the unit for area is square meter, and for volume is cubic meter, which are based on the unit of length. Some derived units and their symbols are as follows. Velocity, which is measured in meter per second. Acceleration, measured in meter per second squared. Force, in meter kilogram per second squared, or termed as Newton. Pressure, in Pascal, or kilogram per meter second squared. Momentum, in meter kilogram per second. Charge, in Coulomb or ampere second, and magnetic flux density, in Tesla, or kilogram per second squared ampere. Let's take a deeper look into these. How can we measure quantities, like lengths, with proper accuracy? There are several ways. Meter rule. It is used to measure the length or distance between any 2 points. As the name indicates, it is 1 meter in length, which, by convention, divided into 100 centimeters. Each centimeter consists of 10 small divisions, known as millimeter. Thus, the smallest reading that a meter rule can give is 1 millimeter, also known as its least count. To have accurate measurements using a meter rule, we must keep our eyes directly above the reading points. Measuring tape. It is used by carpenters and builders to measure a greater length, usually in meter, centimeter, and inches. This means 1 centimeter is the least count of measuring tape. The same as in meter rule, to measure accurately using a measuring tape, we must keep our eyes directly above the reading point. Vernier caliper. To obtain an accuracy of more than 1 mm in our measurements, we use a vernier caliper. It has a main scale and a vernier scale, parts of vernier caliper located on its jaw. A vernier scale has 10 divisions on it, and each division equals 0.9 mm. Thus, the difference of one main scale division and one vernier scale division equals 0.1 mm and is taken as its least count. To gain accurate measurement, we need to find the zero error of the instrument if present. This will help to achieve accurate reading by adding or subtracting the zero error value from the obtained readings. Screw gauge or micrometer screw. It is used to measure small lengths with greater accuracy than a vernier caliper. The least count of a screw gauge is 0.01 mm. It also requires us to find the zero error of the screw gauge. To accurately measure the length, the zero error value will then be used to correct the obtained readings.
Measuring the volume of solids. To determine the volume of a regular solid, such as a brick, first measure the dimensions of the object. Then multiply the 3 dimensions and their units. In this example, we measured in centimeters. Therefore, the units for volume are recorded as cubic centimeters. To measure the volume of an irregularly shaped object, such as a rock, measure the volume of the liquid displaced when the object is submerged. To do this, measure the initial volume of water in a graduated cylinder. Submerge the irregular object and measure the final volume of the water. The difference between the initial volume and the final volume is the volume of the object. In this example, the initial volume is 50 milliliters. Dropping the rock in the graduated cylinder causes the water level to rise. The final volume is 81 2/10 milliliters. To find the volume displaced, subtract the initial volume from the final volume. Doing so yields 31 2/10 milliliters. So the volume of the rock is 31 2/10 milliliters. Typically, the reason to measure the volume of an irregular solid is to determine the density of the solid. Density is the mass of a substance per unit of volume. The formula for density is mass divided by volume. You could also find this formula by looking at the formula chart. Using a balance to measure the mass of the rock, we determine that it is 74 88/100 grams. Since we know that the volume of this rock is 31 2/10 milliliters, and the mass of the rock is 74 88/100 grams, we can calculate its density. When we divide the mass by the volume, we arrive at 2 4/10 grams per milliliters as the density.
In this tutorial, we will learn to calculate the approximate area of a given irregular figure using a square grid paper. Calculate the area of the given irregular figure. Take area of one square to be 1 square centimeter. Step 1. Count the complete squares as 1. Let us color the complete squares orange. Number of complete squares is equal to 18. Step 2. Count the squares which are exactly covered half as 1/2. Color the half squares green. Number of half-filled squares is equal to 4. Step 3. Count the squares which are covered more than half as 1. Color these squares yellow. Number of more than half-filled squares is equal to 7. Step 4. Ignore the squares that are covered less than half. Area of 18 complete squares is equal to 18 into 1 square centimeter is equal to 18 square centimeter. area of 4 half-filled squares is equal to 4 into half square centimeter is equal to 2 square centimeter. Area of 7 more than half-filled squares is equal to 7 into 1 square centimeter is equal to 7 square centimeter. Therefore, area of the irregular figure is equal to 18 plus 2 plus 7 square centimeter is equal to 27 square centimeter approximately.
Calculate it. So what is it? Simply put, density is the amount of a substance contained in a measured 3D space. We call that volume. Volume is usually measured in cubic centimeters or milliliters. So what does volume have to do with density? A lot, actually. Density is how much mass of a substance you can have in a volume. We notice different densities without even thinking about it. You would be more willing to carry a block of foam up a mountain than an equal volume of lead. You can have a large object with very little mass or a large object with a large mass. The higher the mass per volume, the higher the density. So if density is the amount of mass in a volume, then dividing mass by volume tells you how much mass is in that volume. The official equation is density equals mass divided by volume. Now let's see how this actually works. Let's calculate the density of some pancake syrup. First, we will measure the mass of our container. Then measure out 50 milliliters. Next, we will use a scale to find the mass of the syrup. Time for some math. Subtract the mass of the container from the mass of the container with syrup. That gives you a difference of 63 grams. So we have 63 grams of syrup. Finally, we take the volume of 50 milliliters and divide it by 63 grams. The resulting density of the syrup is 1.3 grams per milliliter. Let's do another one, the easy way. How about water? If you have a fancy digital scale like this one, the easy way to get the mass of the water is to use the tare function. Place the container on the scale, then press tare. Now add 50 milliliters of water to the measuring cup. The scale does the work and gives us the mass of water. I have 53 grams. Now we do the calculations. We divide 53 grams by 50 milliliters. Our water has a density of 1 gram per milliliter after significant figures. Now we will do one more example. Let's do vegetable oil. Measure the mass, 45 grams. We have a volume of 50 milliliters. Divide the mass of 45 grams by the volume of 50 milliliters and we get the density, 0.9 grams per milliliter. To demonstrate how these different densities affect one another, let's pour these different liquids into a glass and see how they affect each other. The least dense substance, oil, floats, followed by the water and syrup at the bottom. The least dense substance's atoms are unable to press through the denser substance. Thanks for watching. Please like, comment, and subscribe.
So let's say you have a rectangular object and you want to find the density of it. And if I give you, the length, the width, and the height, and the mass, this problem is pretty easy, right? Because you just multiply length, width, and height. That gives you your volume. And then density is the mass divided by the volume, and you're done. So that's not what this video is about. This video is about that occasion when the object isn't a nice rectangle. So let's say the object is maybe, I don't know, some kind of a rock or something, and it's got this weird shape. So how do you find the volume of that? Well, I mean, you can't measure length, width, and height. I mean, you could, but there's all this empty space around here, so that would not be adequate. So we need to find we need to find some other way to get the volume of this object. So what we can do is we can take this object and we can throw it in some water. So if you have a graduated cylinder, let's say it's got a volume original of 20 milliliters, so we'll call that, VO, the volume original. And so let's say once you throw this rock in, let's say the water rises up to a volume of, how about we say it's a volume of 25 milliliters. So we'll call that VF. So what we need here, to figure out the volume of the rock, the actual size of the rock, we just take the change in volume, and that's VF minus VO. So 25 milliliters minus 20 milliliters is 5 milliliters. So this is the volume of our rock, and I gave you the mass. So now we can just do our density problem. D equals M divided by V. So we've got 10 grams divided by a volume of 5 milliliters. That gives us a density of 2 grams per milliliter. So that's how you solve a density problem with water displacement method.